Fov-GS, Foveated 3D Gaussian splatting for dynamic scene. Rendering quality and performance greatly affects the user's immersion in VR experiences. In this paper, we propose Fov-GS, a Foveated 3D Gaussian splatting pipeline for monocular dynamic scenes and real-time rendering. Here are two views on VR HMDs, which are synthesized with our Fov-GS. 3D Gaussian splatting achieves photorealistic rendering with speeds of over 100 frames per second in static scenes. DGS extends it to dynamic scenes, but the rendering performance is inefficient, with frame rates dropping below 10. Our method not only achieves better visual quality, but also achieves real-time rendering. Compared to the state-of-the-art method, our method achieves higher quality in the foveal and salient regions. The lower left of the left image shows our result, the upper right shows the ground truth. The right are the close-ups of the results. DGS renders full-resolution images, while our method renders foveated images. Compared with the DGS method, our results are closer to the ground truth and preserve sharper details in both foveal and salient regions, especially for the dynamic objects. We propose a 3D Gaussian forest representation that represents the scene as a forest. Each tree within this forest has the same layers, with layers determined by the characteristics of human visual system. Different layers corresponds to different levels of detail. Gaussians at the same layer across different trees correspond to the same levels of detail. Trees are categorized into static and dynamic trees, and only dynamic trees need to be deformed. To construct the 3D Gaussian forest, we introduce a dynamic-static separation-based 3D Gaussian forest initialization method. This method first initializes the 3D Gaussian with SFM points and trains the initial Gaussians. Then this method distinguishes between dynamic and static Gaussians and constructs the dynamic and static forests separately. Subsequently, we propose a 3D Gaussian forest optimization method based on the deformation field and Gaussian decomposition to optimize the forest and deformation field. Based on the dynamic mask, this method first optimizes the deformation field and the dynamic forest separately. Then, based on the static mask, this method optimizes the static forest. Here are images rendered with dynamic forest, static forest, and whole forest, respectively. Next, we present an HVS models-based 3D Gaussian forest rendering method to achieve real-time foveated rendering. This method first selects and deforms the dynamic forest based on the acuity model. Then it selects dynamic and static forests based on the contrast sensitivity function model. The foveated image is rendered based on the selected Gaussians. In the experiment, we compare our method with the ground truth, DGS, and MSGS. DGS renders full-resolution images. Our method and MSGS render foveated images. Compared to DGS, although our method uses fewer Gaussians for rendering, our results demonstrate higher similarity to the ground truth, such as the blue flame of the blowtorch in the foveal region. Compared to MSGS, our results are closer to the ground truth in both foveal and periphery regions, such as the text on the blowtorch and the flames on the chocolate. In the Americano scene, our method also achieves higher rendering quality in the foveal and salient regions. Our method renders the flow of coffee into the cup, the diffusion of the coffee into the water, and the handheld cup, with more detail. In conclusion, we proposed a foveated 3D Gaussian splatting method for dynamic scenes and real-time rendering. Compared to existing state-of-the-art methods, our method not only achieves more realistic rendering quality in the foveal and salient regions, but also dramatically improves rendering performance. Thanks for watching.